This is a joint work of physicists from the Hungarian Academy of Sciences and biologists from the Hungarian Natural History Museum. The striking iridescent colors of butterflies are often caused by photonic nanoarchitectures and not by pigments. The scales covering the butterfly wings are built mostly from chitin, and for the case of butterflies, which are called blues, these chitin plates contain little tiny air bubbles. Light is reflected and refracted on each of these tiny bubbles, and the collective interference effect can be positive and negative depending on the wavelengths of the incoming light. Hence, the different components of white light are transmitted and reflected differently, and we perceive a color. The reflected spectrum, thus the color, depends on the sizes and shapes of the air voids and on the refractive index of the two constituent materials, chitin and air. When we apply a drop of ethanol on the wing, the color changes because the ethanol penetrates the air spaces and the refractive index of ethanol is greater than the refractive index of air. This color change is reversible. When the ethanol evaporates, the original color is restored. This phenomenon, the reversible change of color, also occurs when the butterfly wing is subjected not to a liquid, just to the vapor of the liquid. This is caused by the interesting physics of the tiny holes. If the hole is tiny enough, say in the order of several tenths of nanometers, vapor condenses into liquid well below the saturation pressure in air. This phenomenon is called capillary condensation. The amount of the condensed liquid depends on many factors, but mainly on the size of the bubble. Smaller holes are filled faster than larger ones. In order to study the details of this phenomenon, we choose an exceptional butterfly species, Albulina metallica from the western Himalayas. Most of the butterflies have iridescent colors only on the dorsal upper surface of their wings, and the colors on the ventral lower surface are painted by pigments. Not so for the male specimens of Albulina metallica. Both of the wing surface colors are produced by photonic nanoarchitectures, and moreover the structures are similar. Only the sizes and distances of the air voids are a bit different on the two surfaces. This explains that the dorsal side is blue and the ventral side is gold-green. It is not easy to reveal the three-dimensional structure of a butterfly wing scale because of its tiny dimensions. One has to carry a careful correlated examination of the scanning and transmission electron microscopy images for that. Indeed, the biological photonic nanoarchitectures are not as regular as crystals in solid-state physics or artificial photonic crystals made by three-dimensional lithography. They always contain some randomness. In order to tackle this problem and reveal the order in the disordered structure, we developed a statistical procedure called direct space averaging. During this procedure, we average the environment of each of the air voids found on a micrograph. This averaging indicates the signal-to-noise ratio, and the real structure emerges from the noise. When applied our DSA algorithm on the TEM images of the butterfly Albulina metallica, it turned out that the photonic nanoarchitecture is composed of layers of two kinds. We call them A and B layers. Both the A and B layers do contain air voids, but these air voids are larger in the A layers than those in the B layers. This has a number of consequences. First, the average refractive index of the A layers is smaller than that of the B layers. On the right of this figure, the average refractive index of the layers is symbolized by different shades of gray. A darker shade means a larger index of refraction. Second, the vapors condense more easily in the B layers because the B layers contain smaller holes. This means that when we increase the vapor concentration, the average index of refraction of the B layer begins to increase first. These findings already make it possible to understand how and why the reflection spectra change when the butterfly wing is subjected to ethanol vapor with different partial pressures. In order to fully reproduce the measured spectra, we need a few other important ingredients. Firstly, butterfly wings are not only composed of chitin and air, but they also contain melanin, which is a kind of brown pigment. In order to build a realistic optical model of the wing, we have to include the wavelength-dependent absorption of the melanin. Secondly, chitin itself does not remain unchanged when subjected to vapors. It swells, meaning that the characteristic sizes of the photonic nanoarchitecture increase. Thirdly, in reality, the air voids are not closed. There are horizontal and vertical channels connecting them. Vapor can penetrate the structure through these channels. Hence, the optical model of the photonic nanostructure applied in our calculation was like this one in this figure. This figure shows only the network of the air voids. The space between the air voids is filled with chitin. Now we only have to combine these ingredients. The vapor pressure dependent condensation of the vapor in the large air voids of the A layers, the vapor pressure dependent condensation of the small air voids of the B layers, the vapor pressure dependent swelling of the chitin, and the wavelength dependent absorption of the melanin. As we can see in this figure, this model can nicely reproduce the vapor-dependent reflectance spectra of the butterfly Albulina metallica, both on its two wing surfaces. The measurements were done in the visible and near UV range, and the calculations were done by solving the three-dimensional Maxwell equations. This phenomenon, the vapor-dependent change of the optical spectrum of photonic nanoarchitectures, has an important technological application. It makes it possible to fabricate vapor sensors with optical readout without the need of electronic components. As we showed elsewhere, these vapor-dependent color changes are substance-specific, selective, too. For example, the change of the spectrum is different in case of different vapors, which is a quite useful property for the technological point of view. The support of the Hungarian OTKA grant is gratefully acknowledged.